This is the second half of video 9. In the first half, or video 9a, we defined a rational number in two different ways. One as a repeating or terminating decimal, or equivalently as a real number, a decimal number that could be expressed as a fraction. So we should be able to take any fraction and change it to a decimal form, and it will be either terminating or repeating, or we should be able to take any terminating or repeating decimal and express it as a fraction, since they are two equivalent definitions. In video 9a, we learned how to express fractions in their decimal form, repeating or terminating decimals. And now in video 9b, we will see how to express repeating or terminating decimals as fractions. The first case we're going to do is when the decimal is terminating, or you could say repeating zeros. For example, 1.22. This is the real easy case. 1.22. Well, you'd like to get, integers don't have the decimal points at the end. We don't write it. So notice if I multiplied that by 100, I would get 122. So I'm going to multiply it by 100, but that would make it 100 times bigger. So I'm going to multiply it by 100 over 100, which is 1. Doesn't change a thing, and we get 122 over 100. And there it is represented as the quotient of two integers. Now, I'm not going to worry about reducing it to lowest terms. As you know, quotients of integers, fractions, have infinitely many ways to write them. And we can reduce it to its lowest term, which is unique, but we won't. Okay, the next one is exactly the same kind of problem. We have 1.0003. And I know that to move that decimal point to the right, I would want to multiply that number by a 1 with 4 zeros, 10,000. So I'm going to multiply it by, you could write 10 to the 4th, by the way. I'm going to multiply it by 1. Because then, if I multiply it by 1, I can say equals. Multiplying by 1 doesn't change anything. And when I multiply the 10,000 to the 1.0003, I get 10003 over, and the 10,000 is in the denominator. I mean, you can think of this as over 1, right? Multiply the tops, multiply the bottoms, you get this. And again, maybe we could reduce it. I don't think so. In fact, I'm sure not, because 2 and 5 are the only primes that go into 10,000, and they don't go into the top. So that one is in reduced form. Well, now we want to learn how to change numbers that are repeating, rational numbers that have repeating decimals, into fractions. We know that all rational numbers do have a representation as a fraction. Well, what do you think that 0.9999 repeating forever is? Look at this sequence of numbers up here. All of those numbers are less than 1, aren't they? Even if we had 0.9 followed by 100 more 9s, it's still a hair less than 1. So what do you think it is if the 9s repeat forever? Well, I'm going to prove to you that it is actually equal to 1. And here's how we'll do it. Now, keep in mind, 2 or 3 slides later, I have a method of doing this all written down for you. But instead of writing the method first, I just want to do these and let you see how it works. First thing I want to do is give the number a name. N equals 0.999 repeating. And then I want to circle the repeating part of the number. In this case, it's just 9. And I'm going to multiply n by the number that, the power of 10, that would move the decimal point to the right of that repeating block of digits. So that would be times 10. So 10n is equal to 9.999 repeating. And now I'm going to subtract n from it. In other words, I'm going to subtract 0.999 repeating, and I get 9 of them. 9n is equal to, and now look what happens here. All of the decimal part of the number drops out, and I get 9n is equal to 9, and this tells us for sure that n is 9 over 9, or 1. So this number is equal to 1. And these are the only kinds of numbers that have different ways of representing it as a decimal number. Let me kind of write that in the margins here. All real numbers that eventually repeat nines have two decimal forms, two ways of writing them. For example, 3.219999 repeating is the same thing as 3.22. They're equal. We can express decimals repeating nines in a terminating decimal. And those are the only kinds of rational numbers that have two ways of writing them as a decimal. We know that as a fraction, you can write something, like 1/2. We could write it as -2 over -4. We could write it as 100 over 200. There's infinitely many ways to write this number as a fraction. And that particular number, there is only one way to write it. Well, no, there isn't. It's a terminating decimal, so 0.5 is the way we would choose. But we could also say 0.4999 repeating forever. Terminating decimals can be written with repeating nines, but we don't ever do it. I just want you to see that the decimal representation of a number that repeats nines is not unique. And we'll do another example, changing repeating decimals to fractions. Here's our number. Let's give it a name. First, do that. It's worth it. 3.2222 forever. And circle the first repeating block of digits. Here it occurs right after the decimal point, and the block is just one digit. And I usually draw a little arrow like this. I know I'm going to multiply that by 10 to the 1, or 10, to move the decimal point past the first repeating block of digits. Now, I'm not going to write up here on that number. I'm going to write 10n, a new sentence. 10n is 32.222 repeating. Now, if I just subtract n the way I did in the last example, notice I subtract 3. Notice you have to line up the decimal points. Subtracting. And I have then, again, 10n minus one of them is 9n. And all of the decimal part goes away. And when we subtract, we get 29. n is equal to 29 over 9. So this number here, 3.222 repeating, is 29 over 9. Here's another example, a little bit different. Let's give it a name. Take the time to do this. 0.012112, etc. Okay, so let's circle the first repeating block of digits right here. And so this time we're going to, in step 1, we'll multiply by a power of 10 to move the decimal past the first repeating block. So we'll have to multiply it by 10 cubed. In the second step, we're not going to subtract just n, we're going to subtract 10n. We're going to multiply this by 10. I want to move the decimal point to the right end of the block and to the left end. In the other two cases, the decimal point was already at the left end of the first repeating block. So let's see, we have 1000 n, multiplying it by 1000. What we get is, well, it's 12.1212, etc. And we want to multiply it by 10. So being very careful now, look, I have to line things up so that when I subtract, I don't make a mistake. Multiplying it by 10 is just 0.1212. Point, or you could put 0 point, repeating. Now you can see why I wanted to multiply by 10 in step 2. I didn't just subtract n. If I had done that, these repeating digits here would not have lined up. And so when I subtract, I get, well, how many n's? I have 990n is equal to, and I subtract over here, all of the decimal part goes away, and I simply have 12. So n is equal to 12 over 990. And yeah, you could reduce it, but you don't need to. I just want you to know how to take a repeating decimal, change it to a fraction. How to take a terminating decimal, change it to a fraction. And how to change a fraction to a decimal. On this slide, I just have the exact method written out. If you need to write it down, just put it on pause and write this down. But in each of the 3 examples prior to this slide, we gave the decimal number that we were given a name, and I called it n. Gave it a name. And I circled the first repeating block of digits. I multiplied that number by a power of 10 that will move the decimal point past the first repeating block. In step 3, I'm going to subtract a number that I made by multiplying by the power of 10 that moves the decimal point to the front of the first repeating block. In example 1 and example 2, I didn't have to do that. I just subtracted n. But sometimes you have to multiply that by something in order to get the decimal parts of the two numbers exactly the same, to the right of the decimal point. Subtract and solve for n. So you could write down these steps and back up and go through the last 3 examples and see exactly how I used those 4 steps. In examples 1 and 2, I didn't need to use step 3. Okay, so now let's consider irrational numbers. The real numbers are made up of rational and irrational only. So if the rational numbers were numbers that could be written as a fraction or alternatively defined as a repeating or terminating decimal, then irrational numbers are simply not rational. So they would be, an irrational number is a number that cannot be expressed as the quotient of 2 integers, cannot be expressed as a fraction. Or we could say, alternate definition, irrational number is a number that is a non-repeating decimal. So let's just look at some examples. Well, you know a couple of examples, pi, and let's see, I looked this up, I don't know all these. 3.141592654 ... You can see there's no repeating there. Pi is irrational. It cannot be expressed as a fraction. And of course we have our new number phi, which we know is 1 plus the square root of 5 over 2, the golden number, golden ratio, which is 1.618033989 ... never repeats. And There's many ways that I could form an irrational number just making one up out of my head. For example, how about 4.010010001 ... Can you see that it repeats a pattern, but it's a pattern that makes the decimal non-repeating. There's no single block of digits that keeps repeating. So these are irrational numbers. So this kind of reviews what sets of numbers we've talked about in MAT 103. The real numbers is the big set. That's all decimal numbers. And it has two kinds. It has the rationals, and rationals are the numbers that any of us actually ever deal with. We don't deal with exact representations of irrational numbers because we have to round off at some point to use the numbers. We have to change them to being rational. So, but we have rationals, irrationals, and then the rational numbers are the numbers we've been working in so far. The natural numbers we called capital N, and they were just the counting numbers, 1, 2, 3, etc. And we saw several sequences in those. We looked at the prime numbers, the Fibonacci, the Lucas. We've looked at the evens and the odds. The natural numbers, the integers, is the set containing, and I'm going to put 3 dots to the left, -3, -2, -1, 0, 1, 2, 3. So that's the next set that you learn about in school. First you learned about the natural numbers, and then you learned about 0 and the negative numbers. Those are called the integers. You need to know the names of these sets. And today we have talked about the rationals and the irrationals, and together they form the real numbers. So I'm going to end this video with 2 problems. And you'll see problems like this on our in-class set that we work on, and also probably on the next test. Find a rational and an irrational number between these 2 numbers here, these 2 terminating decimals. Okay, the way I do this is I write the biggest one on top, so I compare the digits and I see they differ right here. So the biggest one is 1.0026418, and it just continues with zeros, doesn't it? You might put in a few if you want. And now I'm going to leave a little space, and underneath it I'll put the smaller of the 2 numbers, 1.00264. Notice I'm lining up the oops, sorry, that should be a 7. 0, 0, 0. So I write the 2 numbers down, the smaller one underneath, and now I'm going to insert a number between. Trying to get... Okay, so let's insert one in between. We know that it will have the same digits out to where the digits are different. And now I want it to be bigger than the number underneath and smaller than the one on top. So I'm going to have the digit 7 here. If I put 8, anything I put after it would make it bigger than the one on top. And now I could put any digit I want here. Oh, let's just put 5. And we have a rational number. It's terminating. So my rational number, I'll put rat, might be 1.0026417.5. Now you could have, instead of 5, you could have 003 if you want, or you could have 6, whatever. But this part of the number would have to be the same in your answer. Now for an irrational number, as soon as I have the rational, it's easy. I'll just put the same thing, and now I'll put a tail on it, an infinite non-repeating tail. How about 0, 1, 0, 0, 1, 0, 0, 0, 1, ... So once you have the rational, you can just put a tail on it and get an irrational number between the 2. And then this is just a little problem to see that you clearly understand the definition of irrational and rational. Write a rational number having only digits 1 and 5. Well, that's easy. I could write 1.5, or I could write 0.1515, or 5.1515, or I could write 151.111111. These are terminating decimals. Or I could say repeating decimals. How about let's repeat ones forever? Those are rational numbers using only digits 1 and 5. I wonder, I'm not absolutely... Yeah, I don't think we need to count the zeros after here as digits. This is definitely just using 1 and 5. Okay, but now for an irrational, using digits only 1 and 5, I could have 1 point. How about 5-1, 5-1-1, 5-1-1-1, etc. It's irrational because it's non-repeating, and it only has digits 1 and 5.